there is a good interaction between NIT and your this SBC Roy College.
Yes, it's a. Uh,
Nice.
there are a few more Indian colleges also who
Okay.
have a well relationship with NIT Durgapur.
Mm-hmm. Actually, the regional such institutes should take these sister institutions in their fold and help them to grow.
So,
Hello, Dr. Joshi, Alam Joshi ji, good to see you. Narendra Pathak, Vikram is there. Tapas Mandal. Professor Basu will be joining.
Yes, sir, he will join.
He's joining. Let me see who are the people who have joined. So I suggest Sarit, who will be coordinating this session?
The Deepta Chaudhary, sir.
Deepta Chaudhary ji. Okay. So Deepta ji, you will introduce Professor Ghatak. Okay, good. And anybody else is there among the audience who would like to mention? Just have a look.
Sir, let us wait for 2 minutes more because it is now.
Only in the conference only. So far as the planner conference is concerned, we are able to.
Okay. Good. And you have fabrication facilities also there?
Working in RF and microwave domain.
Okay.
At TCS research in the domain of millimeter wave radio design and radiating systems. Welcome, sir.
Thank you for your nice introduction. I am really honored in this particularly workshop to be a part of the speakers. And I'm also honored that this session will be chaired by a renowned scientist like Professor Lalit Kumarji. And I have some of my peers from my days at CD. So Joshi sir is there. And I also thank the first call I got from Dr. Anivan Bera, that he told that some IEEE Electron Device Society is going to conduct this workshop in his Dr. Pisida Engineering College. And obviously, I cannot help if I don't mention the whose continued support and encouragement we receive, and time to time, whenever we happen to meet somewhere in physical mode or mainly during the past few years in online mode. So I think that I should start my deliberations, and I shared the abstract title, which is kind of a storytelling for the journey which we had from since 2004 in this domain, when we picked up certain areas so far as the artificially engineered materials are concerned. Please confirm whether you can see the screen.
Yes, it is visible.
Yeah, thanks. So before I go to the exact topic, we like to go for a short decrease into what will be generally the physicists saw about it uh, from quite a uh, considerable time, but we could not get into the experimental verifications of those. One such was the fundamental publication made on backward electromagnetic waves by Mandelstam, and his work was somewhere uh, reported in 1944, but very few people knew about that. The principally, it is generally, if you have seen the very well-known equation where we try to find the group velocity, the k, or it will be the wave vector will be opposite to the group velocity is added along a vector k, and it will be opposite when the sign of d omega by dk will be negative. Now, this, though easily said, is really difficult for us to uh, realize. And some part of these materials with negative parameters as backward wave materials were generally mentioned in Shivukin's work on optical spectroscopy reported in 1957. And obviously, most of the textbooks which beginners read, and we see most of the papers, it mentions about Vesalius. No need to mention, his name is widely known now. Whenever, whatever paper we read, we see the mention of Vesalius about the wave propagation in media with simultaneous negative permittivity and permeability. Now, this took 30 years to be exactly demonstrated by Penry and Smith et al. To show that what were the left-handed materials. Now, the other names that came to be classified as negative refractive index media, backward wave media, double negative media, and also sometimes it is called as Vesalius media. Now, Penry proposed a magnetic analog of an electric conductor with controllable electromagnetic properties, and the first metamaterial definitions was coined by Trauning in somewhere in 2001. But there were many controversies of them. If you read the Ben Monk's book, Metamaterial Critic, it also gives some critical aspects of why we should call it as itself a material. Now we generally even classify the material into, depending on what should be the permittivity and permeability, and we go for some what we call as the conventional materials whose permittivity and permeability will be positive. Now, if it is the permittivity is negative, then we generally call it somewhere as plasma and fine wire structures. Then, if you have microstructures with split ring resonators, it's a negative permeability. And obviously, we call it where both we can achieve negative permeability and permittivity. We prefer to call them as a double negative group of materials. And here, what is the catch? That's the metamaterials. But some of the other, the bookish information has been a little bit left around. So we generally prefer to have a slight peek into the core microwave engineering textbooks we generally follow. If you read about the ferrites, you will find that in the resonances, it is the permeability is negative. For silver, gold, and aluminum, they display negative permittivity at optical frequencies. Now, this is all about the phase of the permittivity and permeability, how it transforms it to give a negative refractive index. But if you want to see the properties, clear insight, if you take the generalized Snell's law for double positive media, it is where the yellow arrow will be followed, and the green arrow shows that how the refraction takes place for double negative media. How to use it? Because these are the things which are fundamentally, these properties are well accounted for and well documented. But how to use them is generally, this is one of the cases where the focusing effect, and it has become a very important tool of making lens antennas. So you have any kind of a radiator which may not have such a high gain. You create a left-handed slab and you try to improve its gain. It becomes more compact also. So these theoretical insights, though these are very fundamental in nature, the initial period, which I kept in the prelude, were mainly the discussions where physicists they tried to give mathematical uh, account for the exactly how the waves are going to interact, how the material is going to behave, and what should be the new way we should look at the electrodynamics where the left-handed media comes. But if you see the practical applications, they have a little bit more intricacies and skills that we need to incorporate. And that's the reason that I thought that I should keep my tutorial in this name, that is the metamaterials and metasurfaces, the exciting route to manipulate electromagnetic behavior. Now, how we manipulate them will be depending upon how we generally go for the application and how much we have peripheral knowledge. So if you want to use the metamaterials for certain segment of your work, obviously it interrelates with various domains. It's truly interdisciplinary research which is getting enunciated with the such kind of a inclusion. If you take the microwave and terahertz technologies, fundamentally from the electrical engineering with classical electromagnetics, with optics in one domain, going for the optoelectronic side. If you go to the higher frequencies, much higher in the terahertz domain, obviously you have to borrow principles and skills from nanoscience and technology. And in some part, the semiconductor engineering also comes into play, where in certain cases, if you want to have an high impedance surfaces, there are cases where uh, metam surfaces have been used as the high impedance surfaces in integrated circuits. So the fabrication complexities, the kind of access to technologies you have will depend on the kind of uh, contribution you can do. Like when we started much initially from the 2004, we didn't have access to such um, intricate fabrication processes. So obviously verifying integrated circuits was not possible at that time. Verifying it for very high frequencies, higher millimeter side was not possible due to fabrication limitations. But as we are dealing with sub-wavelength structures, and that is the reason that most of the initial phases, you will see that the frequencies were generally into the well-crowded region of the electromagnetic spectrum from 1 to 10 gigahertz. So the tutorial content would be as follows. I would generally go into the metamaterial as a homogeneous conglomerate of sub-wavelength resonators. This is first important step we should understand that how it becomes a homogeneous medium without which we cannot add the term material. Because when an electromagnetic wave is imposed upon a certain object, that homogeneous characteristics would generally reflect on how it will be interacting with the electromagnetic wave. So naturally, how you create that homogeneous media with these sub-wavelength resonators is crucial of using it as a material. Then the homogeneous modeling. Now, when we create that, okay, it's really sometimes it is very difficult for us to fabricate such a this large array. So if it is a volumetric region, then obviously it will take a large cost also. Now, with the development of tools, obviously the software, computational interactive softwares, the trend was the homogeneous modeling of materials. And in that case, particularly with the growing interest in metamaterials, how we can model them. And we also tried out into the computational aspects like development of an indigenous FDTD code for observing that how the electromagnetic wave propagates through a double negative media. Now, this has obviously been become more mature over the past 15 years, and the upgraded versions of most of the softwares, they now model it quite correctly in most of the cases. Now, usage of the fundamental building blocks in altering the electrical characteristics of devices and circuits is another domain where, in between somewhere in the 2010 to 2020, people went out for that is fundamental units, the subroutine resonators, not as a array but a discrete elements, were being used to tune the resonance characteristics or to add some benefits to the existing circuit characteristics, like they use work out very nice with kind of filters, kind of planar antenna systems. So in those cases, we call it as a metamaterial inspired design. Now we should not call it as a metamaterial enabled antenna. Rather, it should be a metamaterial inspired design where we use a small part or a fractional uh, part of the entire large array to be used as a uh, subvariant resonator, altering the characteristics of the circuits. And finally, the manipulation of the electromagnetic behavior of circuits and systems for the 2D version. And this has been a very remarkable applications have come up. And this is the main reason where the industries also, many industries have shown a lot of interest in this particular domain. Now we consider about this artificial engineered material. You can see it from the book, which is written much earlier in 2005. It was published by Gallows and Ito. So in there, you can see the transmission line models and the transmission line theory point of view for the composite right, left, and transmission lines can be seen there. So the electromagnetic metamaterials can be considered as a homogeneous electromagnetic structure with electrical properties which are not readily available with materials which are which can be synthesized. We don't have a substrate till now. We don't have a substrate we can commercially available which has a negative epsilon. It's not possible for us. They are made from assemblies of multiple element fashion from composite materials, and the materials derive their properties not from the properties of the base materials, but from the effective electromagnetic property of the entire conglomerate. So you deselect the resonators in the X, Y, and Z directions, and you find a volumetric region with spacings quite small compared to the impinging electromagnetic wave. You make it homogeneous, and then you can think of that how the entire system works. Then you can tune it to either negative epsilon materials or negative mu, or with both double negative regions can be created. Now their precise shapes, geometry, size, orientation, arrangement, each of them has been topic of research, and you will find numerous papers, numerous groups around the world. They have brought out different shapes. Omega shape was by Professor Ingata. If you see the different geometries, we'll show you where compact fractal geometries were incorporated for making much smaller, like lambda by 16, lambda by 8, that kind of subvariant resonators. And this tessellated versions, they give the smart properties which are suitable for manipulating the electromagnetic waves for either blocking or absorbing them, enhancing or bending waves. A lot of ways you can have different applications. So if you use it, you can make it as a 3D slab, which is creating lensing action for your radiators. You need not have a huge structure for achieving high gain antenna systems. So on. Wherever your innovation moves forward, you try to apply them. Now, this effectively homogeneous structure, this possesses a very critical issues here, that for different frequencies you work upon, you have to see that where what should be the spacing between them, periodicity which you should choose to make it appear as homogeneous. A quite guideline is that you keep the spacing smaller, somewhere less than lambda g by 4. Now, this effective homogeneity condition generally ensures refractive phenomena, and that dominates over the scattering and diffraction effects. Now, if the condition of effective homogeneity is satisfied, the structure behaves as a real material, and it is electromagnetically uniform along the direction of propagation. With this, then how to create unit cells. We have seen so many, if you look into the literature, it emanates from some fundamental electromagnetic concepts. If you apply an electric field, then you generally get an electric dipole. Similarly, if you apply a magnetic field, it's quite one equivalent case where you get a magnetic dipole. Now, how to implement it? If you consider an sets of electric dipole and magnetic dipoles, you can consider that that particular set will possess some effective permittivity, and the other one will have an effective permeability. Now, this homogeneity is generally created out of the material own characteristics. So far, so good. These were all positive, which is generally available with the materials you have studied. But if you want to implement for some cases where you want to get it, where you want to tune the characteristics where it has some negative epsilon, negative mu, then you can think of individual geometries like the high structures, the split rings, this producing the electric dipole characteristics, the other one, this split ring has a magnetic dipole characteristics. So many of them were generally the reason behind when magnetism without magnetic constraints were proposed by Shelkunov and Fries as the split ring resonators, wherein such effective material media was created. And that is the origin where these ideas translated and helped Bendy to find out that if you keep an array of wires, then you can get negative permittivity with a positive permeability. And the split ring resonators with such an arrangement that you see here will produce positive permittivity and negative permeability. Together, they will produce the double negative media characteristics. And a lot of analysis, theoretical analysis, experimental verifications were carried on from the late 1990s till 2005. And with the development of the softwares, then obviously it translated to other parts where, because if you want to go for such fabrication, only the academic research is quite difficult for us to get such a large array fabricated, and that to some 20 years before. Because such amount of substrates were also very rare for us. So we could generally use it, the help of the softwares to verify them and to exactly see and re-verify. That was what our initial point was, to re-verify the work which was generally reported by Bentley, Smith, I2 and others. So the material characterization was generally proposed with the unit cells. You can see the wire on the other side, the split ring resonators, and you can do the same with any softwares, electromagnetic simulation softwares you have. But mind it, the phase of the E field will determine that which, how you generally create the S21, how do you generally obtain the value of S21. That corrections need to be done in your program when you extract the values of the permittivity and permeability. And we could see You get the values exactly same as those which are reported for the such kind of systems. And we thought that how to even analyze the structures for what was the characteristics, like those who were trying to observe it through a web guide, uh, non-standard web guide. Inside that there is a omega structure. Then what will be the characteristics? So you can see that it has certain passes, times where it is allowed. In certain cases, it is not allowed. So it generally translates into either shifting in the cutoff or changing the values. You want to stop it. You want to keep a band stop characteristic certain region. You want to allow certain parts. You don't allow others. So like that, you can make some analysis. And these were the simulations which were carried out somewhere into late 2004. So you can get a clear insight that what were the results verified. This is in a series of 10 cells which is put in a web guide. You will see the paper for applied physics somewhere in 2004 it was published. So from that we verified this and we could get the similar results which we had obtained. And further, if you see the transmission line models which were put forward simultaneously by ITO, they were also could be initially verified where what characteristics of the artificially engineered transmission line, composite right left transmission lines could be used for which purposes. So that is another way that you can generally fine tune the characteristics of your overall circuit. Like if you feed a CPW line with an antenna and you just place the splitting resonators as a complementary on the other side or a splitting resonators on the same side, then you can generally create some characteristics of stop band at certain frequencies. You can deal with that. So this kind of a manipulation of the electromagnetic characteristics, like stopping certain bands, were generally very, so to say, encouraging during this early 2000, where a lot of components could be developed with that. Not only the stop band characteristics, now we can place it to split a band also into two. Like this, the CRLS transmission lines were used to split the quadrature hybrid coupler performance into dual band characteristics. So this was again a very interesting result which was put forward. So the way we generally approach for multi-band systems, creating stop bands, they were very much assisted with such kind of components which could be used for augmenting the behavior. And that is the initial work which was mainly focused on. And then the miniaturizing the unit cells. Further and further miniaturization. If you go into higher frequencies, if you want to make it compact. So obviously, instead of the splitting resonators, people tried out with the fractal shaped resonators. So this is one of the our research scholars way back in the 2008. He came up with this. The work took some 2 years to get uh, finalized, and finally it was published. Because at that time it was taking quite a long time for the review process. In this, we propose the more curved fractal for the such kind of unit cells. And later on, we could get a lot of miniaturization with it, and we could use that for the augmenting the radiation characteristics of antenna also, which are the metamaterial inspired. But if you consider an array of such kind of unit cells, then obviously it can be put as a metamaterial transmission line segment. But if you use the individual resonators to augment the behavior, then it is a metamaterial inspired. Now, this small resonator concept, which we generally see that it has been a part of the development process of the homogeneous metamaterials or artificially engineered materials, generally has been not limited to this. In fact, uh, the fundamental of microwave engineering, where if you have studied in the undergraduate microengineering course, you will find that the small resonators have been a key to the success of the microwave vacuum tubes. And this is one of the reasons why this domain of microwave, this workshop also comes into that is metamaterial and metamaterial assisted vacuum tube. So somewhere, if you take the flash cavity, it is a re-entrant one. So if you see that the longitudinal electric fields generally needs to be interacting with the electron beam. So to help that, you see this small opposing metallic structures that produces a capacitance, and the rest is the inductance. So the bouncing of electromagnetic EM waves in the cavity is generally on off. So that is not wave. So this is example of a small resonators. We generally don't decide on the work functioning by bouncing of waves from the deflecting walls. Another definitive places of the resonator work functions as a capacitance and the rest as an inductance. So generally we can find the such kind of proposals way back by Hansen and Richmond and Mineri and Emerson. So there we enter in cavity. And in fact, one classical example was the hole and slot type magnetron cavity. So there it is an open structure. It has a gap through which it can interact with the existing electric fields. It's small relative to the bedrock. And this is again a classical example where the capacitance is partly due to the gaps as well as other parts of the resonator. The inductance is due to the horizontal current flowing in the cylinder. Now this is the reason that where the small resonator concepts coupled with the small resonators, which are again electrically small structures in the planar domains. So a wide variety of applications we saw from the beginning, that how metamaterials gradually got a fair position in improving the characteristics. Now, if you move further into terahertz, you will find that people are going into that domain and their computer devices develop. Now, when the next part is first is treated like what is the small resonators, how to make them, tessellate them, and get the entire homogeneous media out of them. And certain small resonators, how to make them further small. In fact, we had fabrication limitation also. We could go for lambda by 60. But there have been reports by Pilotti et al. Who reported some lambda by 74 also in planar, somewhere in the year 2010 or 11. Now, when we go for homogeneous modeling, therefore processor only. So after these simulations were done, I could find that for the electric field, which is horizontal to the XZ plane, is generally passing through as if nothing is there. But if you consider the vertical component, which is directed along Y, and it is oriented along the wires, it is, you see that it is getting absorbed. Much of the impinging electromagnetic wave is absorbed. So this kind of observations raised more curiosity that how it can be used for signal augmentation purpose, and also how it can be used for enhancing the properties of existing electromagnetic compounds. And came the thought process that if we take it in this way, if you model it, then it takes a lot of time for simulation. So instead of going for the structure, it was well accepted by that time that okay, array of wires and split ring resonators will make a TNG material. So how to model it? So then it came the advent of the crude and Lorentz models, which helped us in the homogeneous modeling of the metamaterial media. So you can set the parameters. Now it is quite well documented in the literatures which are available, but it got noticed when the Thomas Wayland published this extraction of effective material parameters by parameter fitting of dispersive modes. Now, this in 2007 it was published, and by the time CST was having the crude and Lorentz models incorporated, and we verified that paper and for the wedge shift that in which and the how it is showing negative reaction for the region where it is the electricity pattern. And we got it published in July 2012, nurtured the effects of the DNG materials on the microstrip antenna with the taking the route of homogeneous model. And we could get some interesting results where some cases it was splitted, it becomes wide, it could go for dual band, we could enhance the gain. So different combinations were triple amount of time. So we want to explore the auxiliary differential equations for in the MPTD analysis of PNG material. So the wave fronts you see they're oppositely traveling inside the DNG material. These results were also published with a different modeling software uh, by Ingata et al. But we verified with our own developed code. And it was also quite fast in with the use of auxiliary differential equations. And we could get the feeling that exactly the mathematical insights are giving us results of backward wave propagation. Now, we come back to utilizing the unit cells which were used to tessellate and make the homogeneous material media. The initial microstrip antenna, it's obviously you can see the radiation characteristics at the lower frequency. It is having just as the radiation catches of a microstrip antenna. Other one, it is having a other plane where the radiation maxima is high. So we can use it for transmitting two different information at two different frequencies, which was quite likely to be used in the much later practical domain of MIMO antenna systems. So there, it can have a very effective applications where we can say two different information in these two different frequencies, or in the same frequency having different radiation characteristics. So people also tried out. There are a lot many such metamaterial inspired antenna geometries also are available in the literature. Now we use that Hilbert monopole with the Volkoff split ring resonators and augmented the radiation characteristics, added the modes. Though without the subwavelength resonator, it was not radiating at a particular frequency. With the subwavelength resonators, we could add on to known number of frequencies in the vicinity of the main radiator. The coupling was so strong that the radiation also was quite considerable. It's not that the gain was much less. So that kind of augmentation we could do for loading of the metamaterial subwavelength resonators to augment the resonance characteristics of certain such radiators. Last part, which I want to mention as a direct consequence of the fact that what would happen if we have a single layer where we tessellate the subwavelength resonators. This borrowed two concepts. One is what is borrowed concept of the volumetric metamaterial. The other concept was from the frequency selective surfaces. Then does this meta surface is a true frequency selective surface? In a frequency selective surface or electromagnetic band gap, the resonators are comparable to wavelength. But if you consider a metamaterial, then the resonators are very small compared to the wavelength. Sub-wavelength resonators. They're small resonators, simply speaking. And it's produced certain beautiful characteristics of manipulating the electromagnetic waves or the electromagnetic characteristics of a existing radiator. It soon became a widely accepted view, and I think now many people are into the domain where they're working out the metamaterial to the 2D version of a meta surface. Now, it's a simply speaking, it's a 2D version of the volumetric metamaterial. Like the metamaterial, here suborganized structures are periodically arranged to realize the surface. As much of the ideas are borrowed from frequency selective surface, they're also considered as a variant. Differential phase control for painting on the surface is important in both fundamental EM research and that there are many industries have shown a huge interest in this particular domain. And in fact, we are seeing that certain cases where for the millimeter wave 5G systems, in fact, certain companies have gone for we can take a giant leap forward in implementing them for integrated circuit domains, which will be really very innovative products. And we have a huge manpower who are ready to jump into this particular domain. And that's the reason that I was so interested for this, to make a route to training these people also, training the new generation so that they can take this leap. But one thing is that, which probably in the last slide when I deal with the further reading part, I would mention that where is the gap. So when we take about the meta surfaces, how it came into its present reality, if we take a PEC, we can make it a short circuit transmission model. It has a deflection phase of 180. For a PMC, it's 0. But for a meta surface, we can tune it from plus 180 to minus 180. So it behaves at certain frequencies, PEC behaves at certain frequencies, PMC. There is a resonance frequency also. And therefore, we can use it to manipulate the electromagnetic behavior with this kind of a 2D surfaces. Not only we could manipulate the electromagnetic wave propagation for bending, for volumetric regions where it will be absorbed, but retransmitted from the meta surfaces, their control can also be considered as manipulating the electromagnetic characteristics, and in some cases it's also augmenting this behavior. Now this how here we get the N and C, it's very easy to understand that if it's a metal patch which is shorted to the ground, some series of such metal patches which are sub-wavelength. These are the unit cells individually, and the path you see which produces the inductance and the gap between them producing the capacitance. So you can easily model it. And we can also create a array of such tessellated patches, not only with the mushroom geometries, but with other geometries where the other side is not also shorted. And we can create such reactive impedance surfaces. and we can find the surface impedance for them, which is, you can refer to the, if you want to see the details of calculation of the surface. It is being used for the next generation node block. That is the best